In terms of electric field stress control, the next thing that we will discuss are sandwich dielectric systems or multi-layer dielectric systems. We've already discussed the simplest kind of multi-layer dielectric system, where you have parallel layers of different dielectrics with different material permittivities or dielectric constants, one on top of the other. But remember that if you have a sandwiched or multi-dielectric insulation system, there can be, apart from the fact that it may be able to control the stresses, but it can also render the insulation more dangerous. For example, if you put a material with low permittivity right adjacent to a material with a very different permittivity, then the stress in the lower permittivity material can be exacerbated very largely, and this can become dangerous. We have learned how to calculate, for analytically, for simple cases, when you have a two-layer multi-dielectric system. If you look at this is the expression for E1, which is V, the total voltage across the entire combination of layers divided by the effective distance. The effective distance is different from the original distance and less than the original distance, D1 plus D2 into epsilon 1 by epsilon 2. Less than the original distance if epsilon 1 is less than epsilon 2, and so on and so forth. Here I have a graph which shows how the electric field divided by V by D. V by D is what you would have if it was the uniform field, the mean field. So this is the Schweiger factor. How the Schweiger factor varies with as D1 changes. As D1 changes as a fraction of the total distance, then you have a variation, the Schweiger factor across material 1 and across material 2 changes in this manner as D1 increases. We also have discussed how to calculate the resultant permittivity of a multi-dielectric layer system. For parallel plates, the volume is proportional to thickness, and therefore the resultant permittivity of the composite material for a two dielectric system is 1 by V1 by epsilon 1 plus V2 by epsilon 2. For a mixture of n materials, the resultant permittivity is 1 by V1 by epsilon 1 plus V2 by epsilon 2, and so on and so forth up to V3 plus V3 by epsilon 3, where summation Vi is equal to 1, which means the Vi's are not the volumes but rather the volume fractions. So the V1 is the volume fraction of the first material with respect to the total dielectric of the composite, total volume of the composite dielectric. As you remember, we have already discussed that the reason that we use multi-layer dielectric systems is because when you use a single layer of dielectric, there might be random distribution of weak regions. In these weak regions, you may have an encapsulation of a lower permittivity material. And as we know, whenever we have a lower permittivity material adjacent to a higher permittivity material, the lower permittivity material is in special danger of discharging or breaking down. So when you use several layers, even if you have a distribution of weak points, these weak points are unlikely to form a bridge or a continuous weak region between the two electrodes. Instead, these weak regions will be randomly distributed along the area, and as a result, adjacent to a weak region, you will have a strong region, and on an average, the dielectric is likely to perform better. But this is something that we have already discussed. In terms of multi-layer dielectrics, I would like to discuss the case of a coaxial cylindrical system like a coaxial capacitor. In a coaxial capacitor, inside you have the conductor on which you apply a voltage V. The conductor has a radius R1. The outer radius is, let's say, Rn, and there are several concentric layers of dielectric material. So you don't use a single dielectric material to fill up the entire region between the two concentric circles, concentric cylinders. Instead, you use several layers. So we know how to calculate the electric fields at any point in between this voltage, between this conductor and the earth's outer conductor, where V is equal to 0. Applying Gauss's law to each of the individual interfaces, now we know that Ex is equal to capital V divided by epsilon x capital X summation 1 by epsilon ln Rn plus 1 by Rn, n going to 1 from m. So this is actually derived from the expression that we have already obtained for the electric field for a coaxial cylinders. Now, if you apply Gauss's law to each of the individual interfaces, you will be able to find the E at each of these surfaces. So, each of the interfaces is an equipotential because E only varies with the radial distance from the center. So, if you have a concentric circle, then on the surface of the concentric circle, there will be a constant potential. And Ex is proportional to 1 by x. Discontinuity, so what will happen is the field keeps on varying. So if I start with the first, let's say the first layer, so epsilon 1, and E varies as the distance from the center. It will vary, it will keep reducing, but then when I reach the second layer, my epsilon changes, and as a result there will be a discontinuity. So there are discontinuities in the field distribution at the interfaces. If there was a single layer, you would have an electric field which varies with distance from the center gradually. However, in this case, it starts varying proportional to 1 by epsilon, 1 by x, as well as dependent on epsilon 1. And then when it encounters epsilon 2, at that interface, you will get a different value for E, which will cause a discontinuity. So there are discontinuities within the field distribution at the interfaces. Now what I can try to, so at every point where x is less than equal to Rn and x greater than Rn, you have different expressions for Ex, and two different values appear at an interface. Now what I would like to do is, I want to maximize the utility of my dielectric materials, and therefore even though I know that the permittivities are different, I know that the maximum fields appear at the beginning of a material. So epsilon 1 at the interface between conductor and in epsilon 1, I have maximum field for the layer epsilon 1, and then at the interface between epsilon 1 and epsilon 2, I have the maximum field that I have in the material epsilon 2. What I would like to do is, I would like to equate all these maxima. So at every interface, I have the maximum for the electric field in that dielectric material, and I would like to make each of these maxima equal to a constant value. As the maximum values of Ex are always at the location x greater than equal to Rn, it is possible to maintain the same value of Emax within every layer of the dielectric. And what do I need to do for that? I need to make epsilon Rn constant. So this is what I do. The field is maximum and it starts reducing. It reduces to a considerably low value. And then when I enter into the material with epsilon 2 permittivity, I make sure I design the radius in such a way that the electric field is equal to the electric field at the beginning of the interface 1. Which means the field here is 1. Again the field starts going down, and it will reach a value. And this value may not be equal to the lowest value here. It will probably be a lower value if epsilon 2 is greater than epsilon 1. But what I'm trying to do is, at every discontinuity, I am making sure that the dielectrics experience the same maximum field. And the necessary condition is epsilon 1 R1 equal to epsilon 2 R2 equal to epsilon Rn should be a constant value. This is of course obtained from this expression. So what you have is, in this way we can control the stresses in a concentric multilayer dielectric system. Another aspect of controlling stress or stress being exacerbated is because when you have a flux line in a particular material and it encounters an interface between two materials, then that flux line is going to be deflected. It will not continue to progress in the same direction, but it will be deflected from its original direction of propagation. So let's say this is a material with permittivity epsilon 1, and adjacent to you have a material with epsilon 2. This is the interface between epsilon 1 and epsilon 2. If this is your flux line, this flux line does not continue to travel. So E1 is your flux line in, or electric field line in material 1. If there was no difference between the permittivities of the two medium, in material 2 it would have continued to propagate along this direction. But epsilon 2 is not equal to epsilon 1, and as a result we see a deflection. So this E1 now changes and proceeds along direction E2. If the angle that E1 makes with the normal is alpha 1 and the angle that E2 makes with the normal is alpha 2, then we can write tan alpha 1 by tan alpha 2 is equal to the tan alpha 1 as the ratio of the tangential components of E1, so ET1 by EN1. Similarly, tan alpha 2 is the ratio of the tangential components of E2, which is ET2 by EN2. So ET1 and ET2 must be equal along an interface between two dielectrics. We have seen that as a dielectric boundary condition if there are no free charges present, and therefore if this is always true, of course, I'll come to this point later. ET1 is always equal to ET2, so therefore tan alpha 1 is equal by tan alpha 2 will be in the ratio of EN2 by EN1. And EN1 by EN2 is equal to dN2 by epsilon 2, dN1 by epsilon 1. dN2 is equal to dN1 provided there is no free charge at the interface between the two materials. So ET1 is always equal to ET2, but dN1 will be equal to dN2 only if there are no free surface charges at the interface. So let us assume there are no free charges at the interface. In that case, this ratio becomes epsilon 1 by epsilon 2, which means tan alpha 1 by tan alpha 2 is equal to epsilon 1 by epsilon 2. So to summarize, the electric flux lines or field lines follow the laws of refraction in traveling from a material with permittivity epsilon 1 to a material with permittivity epsilon 2. It will be deflected from its original direction of propagation such that tan alpha 1 by tan alpha 2 is equal to epsilon 1 by epsilon 2. This must remind us of Snell's law for refraction of light. So we call this law of refraction of flux lines. It is analogous. Remember, in practical systems, when you have DC voltages, at the interface, you will have free charge accumulation. In the previous discussions about, for example, concentric spheres or even about these layers, where you say that this is the manner in which the electric field will be divided, and this will be how the voltage will be divided, and these are the electric field. We have always made an important assumption, and this important assumption is that there is no free charge at the interface of any two dielectric materials. Here too, for this derivation, we make the assumption that at the interface between two materials, there is no free charge. This is an unrealistic assumption because at the interface of two different materials, under DC voltage application, there will always be free charge accumulation, or what we call space charge accumulation or surface charge accumulation. Why is this so? This will happen because of the differences in not only the permittivities of the two materials, but also because of the difference between the conductivities of the two materials. Think about it like this. Let's say, apart from epsilon 1 and epsilon 2, you have conductivity sigma 1 and sigma 2. Let us also assume that sigma 1 is less than sigma 2. Now, if you have charges, a dielectric is not ideal dielectric, so there will be some charges flowing into the material. And the number of charges that flow into the material per second will depend upon its conductivity sigma 1. So let's say some charges, let us in fact say that let's say some charges are flowing through material epsilon 2, and I said epsilon 2 is greater than epsilon 1. So epsilon 2 is greater than sigma 2 is greater than sigma 1. So if you charge the system such that current flows into material epsilon 2, and the number of charges flowing per unit second will depend on sigma 2, and some charges will arrive at the interface. Now they will cross the boundary and flow through the material epsilon 1. I say that the material epsilon 1 has a conductivity sigma 1, and I have also assumed that sigma 1 is less than sigma 2, which means the number of charges which will flow from this boundary towards, let's say, the other electrode will depend upon sigma 1. And if sigma 1 is less than sigma 2, the number of charges flowing across this material per second will be more than the number of charges flowing out of the interface through this material per second. So if 10 charges are coming in per second, let's say only 6 charges will be able to flow out. So what will happen to the remaining 4 charges? They will get accumulated at the boundary. So because of the discrepancy between sigma 1 and sigma 2, there will be charge accumulation at the boundary. And this will be you will need to take this account. But right now for these discussions, where we are actually concentrating on the nature of field intensification, mainly due to the difference in the dielectric constants of the material, we will not consider free charges, but in practical situation, we will have to do that. So in practical systems stressed with DC voltages, the accumulation of free surface charges at the interface will take place. Now, forget about the free charges. If you consider the laws of refraction, then certain things will definitely happen. I give here some examples. This is a situation where you have a material with permittivity epsilon 1 and another material with permittivity epsilon 2, and the interface is not normal to the conductor. This is your conductor, and the interface makes an angle greater than 90 degrees with the conductor. As you can see, there is a crowding of flux lines at this point, and this is because of the difference in permittivity. Maybe far away from this junction point, the fields are pretty uniform. The fields are uniform here, the fields are uniform here, but there will be a concentration of flux lines which is very large at this region, around this point P. And depending upon the values of epsilon and epsilon 2, the flux density here, the flux concentration may be so high that there will be considerable local field enhancement and discharges may occur. Similar situations may occur here. This is what is called the ICB electrode system. Generally, this is used for certain experiments. This is an IC standard electrode system, and we will see later for what it is used. This is a rod plane electrode, and there is a chamfering at the edges. Now, in this very small region, there is a very small gap. Here I have kind of magnified the gap, and you can actually see it. In reality, you may not be able even be able to see it. Suppose you have a rod electrode which is sitting here. It seems that the rod is completely flush with the electrode. But what might happen is at the center, right at the tip, there may be an infinitesimal gap present. And in this region, in this very small region, you have air. And air has a much lower permittivity than, let's say, this dielectric material. So you see, normally what we do is we have a dielectric material here. We have a plane electrode and we have another rod electrode. This dielectric material, which is a thin slab that you see here, is sandwiched between the two electrodes. Now, and I am going to perform a breakdown strength of this material. So I want the breakdown to happen here. That doesn't happen. What happens is here, in this region, you have a material with very low permittivity, air, and because this other material has a high permittivity, this region will be stressed considerably. There will be very high field intensification in this particular region. in this particular region, there will be a very high field concentration. And as a result, there will be partial discharge in this region. Partial discharges will occur. So when partial discharge, I'm not being able to rub this out. So when partial discharge occurs in this region, then of course degradation of this material will take place even before breakdown through the volume occurs. So this is just to give you an example that when you have these laws of refraction in place and you have materials with different permittivities in close proximity to each other, many different things can happen, and there can be local field enhancement, and these can lead to dangerous conditions. So we have to be aware of that. So what we can do is we can also use the laws of refraction to our advantage. Just as the laws of refraction give rise to dangerous situation, similarly they can be used, they can be co-opted to ease the stress concentration in particular regions and get a better design. One example of this is in the case of spacers. What are spacers? Spacers, we talk about spacers, let's say in the context of gas insulated lines. Now, as I have mentioned before, gas insulated lines have a conductor, a metal conductor, which is running through the center. It's a cylindrical line. And it has to be, because it is gas insulated, it has to be enclosed in a chamber. So this is a coaxial concentric cylindrical system where you have the conductor as the inner cylinder and you have the outer enclosure as the outer cylinder. The inner cylinder has a voltage, and the voltage will depend upon whatever is the rating of your line, and the outer cylinder is the encapsulation, and that is grounded. And between, so let's say this is your outer chamber, outer cylinder, and this is your inner conductor. The gap between the cylinder and the gap between the conductor and the enclosure will be filled up with the insulating gas, which is generally SF6. But these metallic conductors can be very heavy. Their dimensions will depend upon the rating, and if you have a high rating, then it is likely that these conductors can become very heavy and they have long spans. So what you need is, you also need to provide some mechanical support. Spacers do that. So what you will do is, just as in a transmission line, air is your main air is your main insulation for the air insulated transmission line. But you have the transmission towers which holds the lines in place so that they do not sag, to give it the mechanical support. And there you also have to provide insulators to insulate the lines from the transmission tower. A similar thing has to be done here. So this is your gas insulated line, and you provide a spacer, a solid block. This solid block between the enclosure and the conductor is called the spacer. It must be insulating, so it has to provide the insulation that SF6 provides. So it has a dielectric function. Apart from that, it provides mechanical or structural support to the inner conductor. Now let us say in this picture you see that it has a kind of curved shape. I'll come to this later, but it is not necessary. It could be a simple block like this, a simple rectangular block like this of some solid dielectric material with a high permittivity, which holds the inner conductor in position. Both sides there are spacers, and it is held in position with respect to the enclosure. Now we know that the electric field varies with distance from the center. So if you have a straight block, you would have, these would be your equipotentials. The equipotentials would all be parallel to the conductor. Let's say if you have a perfectly linear conductor, then these equipotentials would be parallel, or concentric cylinders with respect to the inner cylinder. Along this line you have one potential, these are all equipotentials. But because E varies as 1 by x, what would happen is you would have along the surface of the spacer, you would experience an electric field. And at the interface, the electric field of consequence would be the tangential electric field, the tangential field along this region. And this tangential electric field would not be constant along the surface of the spacer because the equipotentials are not uniformly spaced. The equipotentials become further and further apart as we go towards the enclosure, and they are spaced close together near the conductor. So along this surface, the tangential electric field at these different points would not be constant, and therefore there might be, whenever you have non-uniformity, at some point there will be very high stresses, at other points there will be low stresses, and you are not utilizing the material uniformly, and there will be breakdown there can be breakdown at one of the points where the electric field is considerably high. So instead of using a straight spacer block, we can use a curved surface. The spacer block can be designed to have a curved surface. The result is such that due to the laws of refraction, see, no longer you have normal equipotentials do not enter into the spacer normal to the surface. They are refracted, they are kind of bent, and the bending can be such, you design the bending in such a way that the tangential electric fields along the surface of the spacer is constant. The spacers can be, for a straight spacer block, ET is not constant along the surface because there is no bending of the equipotentials. The spacers can be formed in such a way that all the ET components along the interface remains nearly constant, and therefore everywhere throughout the spacer you have more or less the same maximum stress intensification. So this is about our discussion with electric stress control.